Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This project we've been sort of working on for a couple of years. It originated in this ill-fated DARPA LifeLog program. There was a call for proposals about that where they were looking to sort of instrument people and recover their activities. And when I was looking at that, I was thinking, you know, I bet you could do a lot of this just by getting the audio. And so the motivation is to sort of try that out and see how much information and what kind of useful information you can get out of a personal archive if you only have audio recordings. So let's talk a little bit about what we mean by that, and then some of the work we've been doing just to investigate what we can make, or how we can make this work. Segmenting and clustering the audio. We've been looking at detecting the speech segments and looking for repeated events. And I'll talk a little bit at the end about our efforts to develop some tools to make this easier to do. So to me, the fascinating motive is that it's technically very simple, straightforward to make continuous recordings. So this here is an MP3 player. It's $100, and it has a microphone built in. You know, they sort of thought, well, we're going to build this device. We might as well make it possible to have people record lectures or whatever. But because it's got a gigabyte of memory, and it can record easily we can record 30 hours worth of audio. And it turns out that with a single AA battery, it can record for 12 hours continuously. So I can just put this on my belt, turn it on, walk around and record everything, no problem. And when I upload it, it's still only a couple of gigabytes a week, so it's actually very manageable. It's something you can carry around, this audio, and the storage problem is solved. But once you've got these recordings, they're almost entirely opaque. The idea of having this 8-hour recording and trying to find something in it, what are you going to do? You know, you can sort of try and do binary search to try and find a particular point, but it's really painful, really difficult, because to sort of figure out where you are, you have to listen to several seconds of audio, and this is just a very, very awkward process. So the sad fact is, even though I've made a lot of these recordings, I don't have any good stories about times when they're useful. Right? I still haven't really found anything that really is compelling about using them, although that's kind of the thing we're still looking for. And it seems like there's got to be something useful that you can do. There's got to be an answer to this. So the project is to see what kinds of tools we can develop to make these things useful and to help accessing them. This idea of minimal impact has a couple of dimensions. One is that because you're making a recording like this with an audio-based device, so it doesn't have to have line of sight, and it just sort of has to be body-worn, the actual process of recording has very low impact on the person making the recordings. The other aspect is that if you want to, let's say there's a small fraction of this data which might be useful, and you have to make it so that the economics of recording information is sufficient to sort of pay back for that relatively modest utility. So you want to make it very simple for people to record the data and store it and manage it, because if it's any amount of effort and they're not getting a lot of payback, they won't do it at all. So that's another sort of thing we're thinking about. How can we just make it easy to build these kinds of archives? So what kind of information can we hope to get from these recordings? Well, if we have these long-duration recordings, we can reasonably expect to be able to figure out the location of where someone is. That basically, if you're in a particular place for 10 minutes, you've got the recordings of the ambient background noise. That's fairly characteristic of a particular location and activity. So both the place and the kind of thing you're doing, whether you're, walking around, having conversation, etc. Obviously, once we get into the more detailed sound information, we can expect to get information about people. So that can be at various levels of detail, from just generic information, well, there were 2 different males speaking, or ideally more specific information where we actually identify the individual people speaking. This begins to sound like interesting things we could pull out. And then, of course, as we go to another level of detail, we could actually maybe get the words out, which, when you think about it, that's often kind of it's the crux of a lot of this stuff. People have very ambivalent feelings about having that information preserved. but it is clearly information that people care about. Things we can't get, of course, only using the audio, are the visual things, what people and things look like, the things that you can get with a sense cam. And obviously some sort of corresponding attributes, things like the difference between day and night is relatively easy to get out of images, very hard to get from the audio, except indirectly. And things about how things that people do that don't result in sound, so when they look in particular directions, then obviously we can't get information. So we can't get everything, but we can get a lot, and particularly for the kinds of goals of the LifeLog program, which was like trying to describe the sequence activities someone did, this seems quite feasible. So the kinds of applications we're looking at are this kind of automatic appointment book history, this thing which says, okay, during this recording, this is what you did. You had a meeting, you went somewhere else, you had lunch, whatever. When you have a collection of data which is very extended, you can imagine sort of gathering statistics on your life which are, aggregated over a longer period. So how much time do I spend in meetings? What's my pattern of people I speak to? Even things like what are my particular idioms that I use a lot? Things that I don't know if that's important, but it would be kind of cute to be able to get that out. Obviously, there's this obvious thing of if you can recall exactly what you or someone else said, that's sort of what we spend a lot of time doing. So this is one possibility to try and shift the balance there. One thing that sort of came up when we started making these recordings is that there is a funny kind of nostalgia aspect to reviewing these recordings, which is kind of akin to looking at snapshots. And it's interesting talking, what we've heard this morning about the particular link between images and memory. There is also some kind of, my informal observation is there's some kind of emotive link between hearing a particular piece of speech and your sort of, effective memory of that. And that's sort of something that's been very underutilized. But really, we want to understand better what applications could be used for this data. And the way we can try and find this out is by actually collecting the data. Until we have a record like this available, there's no real reason to think about things you could do with it because, well, you don't have the data. So a lot of this project was kind of a leap of faith to say, well, let's just start collecting this data and hopefully we'll figure out something useful to do with it later on. Sometimes I think about the people who want to get their heads frozen cryogenically when they fall sick, because in 50 years' time we'll be able to do all this stuff with that. And I kind of feel like we're a little bit in that kind of ball game that we're thinking, well, we don't know what to do yet, but maybe if we make the recordings now, this is the only chance we're going to get to make those. Okay, so let me just quickly tell you about a few of the things that we've been doing with this data. The first thing we wanted to do was just say, okay, we've got these very long recordings. What is the sort of the coarsest kind of information we want to try to get out of this, which is structuring this thing into a series of slightly shorter episodes which are consistent. And this is something that there are a bunch of tools available that we sort of know how to start doing this. So the idea is, if we try and think about this diary application, can we segment the recording up into these different things that happened? I was in a lecture, I was in a meeting, I was walking home or whatever. Compared to a typical audio analysis problem like speech recognition, this poses some rather different requirements. So typically we have a frame rate in speech recognition of like 100 frames a second. But here we're interested in a much longer time scale, so actually our basic time frames need to be much longer. And we were looking at like 1 minute long time frames, so we're just looking at the statistics of every minute of the recording. If we're interested in these kind of slowly changing attributes, then sort of the background is actually more important than the foreground. So that's why we want to have something that averages out the behavior over a minute, so that the sort of the variation in foreground kind of gets washed out, but the consistent things in the background are the most prominent parts of that information. And then it seems sensible to use perceptually motivated features because obviously we're trying to get at things that people would notice as well. You could argue that both ways, because it may be if there's information that people don't notice but which helps with the task, that could be helpful too. But there was some background and perceptual stuff that we've done. So the kinds of features we were using, so these are spectrograms, that is the conventional time frequency representation. But here the time is like 8 hours or so, or six or 8 hours of recording. And on different frequency axes, these are actually frequency in BARC, which is an auditory, an ear model scale. This is the energy. on average in 2 different domains. And then these are the sort of the variations of energy within each 1 minute frame, which is also a useful kind of second aspect. And then we had this thing which we call spectral entropy, which is related to a lot of other measures, basically how complex the spectrum is within each individual frequency band, so whether it's broadly spread out or focused in a few bands. And this, again, gives us a way to distinguish things which might look very similar in these average energy representations. What we see here is you begin to see, like, there are these big chunks where things are the same, and then there are changes, and you sort of see the logic of trying to segment the audio up into these different longer segments. So we use a technique called the Bayesian Information Criteria, BIC, which is things been used in speech recognition for segmenting different speaker terms. We have a database of like 8 days of recordings, which is about 62 hours. We, meaning my student, hand marked this into sort of 139 different segments, so they're about 20 minutes each on average. And he assigned those to 16 different categories. It was his data that he was marking. And then we basically want to see how well we could actually,
Yeah, but this is something this makes me curious. Because audio is linear, how long did it take him to do this?
It took a long time for him to mark that. I mean, we have a lot more data than this, but this was like the most I could possibly ask him to mark up. In 139 segments is not a lot, but it was very, very
because to find
difficult.
It will be hard even by hand.
Yeah. And of course, when we were doing this, was kind of before we had any tools available. So it was he's a very dedicated student. So we're able to look at different features we're using and measure our ability to recall, to find these particular boundaries that we've hand marked. And actually, this works pretty well. I mean, as you'd expect from those pictures, there's some extent, because he knew what system we were going to use when he was marking these boundaries, this is an optimistic measure, but it seems like we can actually get many of these boundaries pretty accurately. And incidentally, these auditory model features work a lot better than standard MFCC features, which are sort of down here in the recall. Okay, so now we're able to break this recording up into these sort of roughly half-hour-long segments when things are happening. So now we want to sort of see if we can figure out that different segments that we've broken up correspond to the same events. We have these 16 categories of events, and this is the kind of a similarity matrix where we've sorted the 139 segments by the different labels, and then we've shown on the picture here, a black dot means that they're very similar by this measure we're using, which is the KL distance, which is a measure of similarity between probability distributions. And we see that, yeah, roughly speaking, many of these categories are similar to themselves and dissimilar to the others. Although there seems like, for this one, for the restaurant class, there are like 3 different subcategories which are all kind of mutually dissimilar. And some other things, there are clear outliers here that some of these library events are different from the others. But basically that looks pretty hopeful. So then we're able to use a clustering technique called spectral clustering, which brings these things together, finds several different, finds a way of assigning them to similar categories, and then we're able to evaluate that. The clusters we get out are anonymous, but we can sort of do the best job of making them correspond to the ground truth clusters, and then we can measure the correct rate, and we get like 70% correct, which is not great, but it's useful. And so this is a typical result. Here's a 10-hour recording. Here are the actual segments we got automatically. Here are the labels we assigned automatically, where I've sort of given them the actual names that do the best job. And here's the ground truth. And it's not perfect. It's not even that good, but it's getting some useful information out there. Okay, so that was kind of our first experiment, and it was sort of our first exposure to what this data was like and what it was useful for. And one of the things we noticed was that the speech content, which we'd sort of been shying away from because of the privacy problems with it, really was very important and was very interesting and something that we'd want to be able to index and access this data through. So then we started looking at the problem and saying, well, maybe if we can just detect where the speech is in these recordings, that'll be a useful kind of indexing attribute. And sometimes it's maybe useful to detect the speech is present even though the speech itself is not intelligible. So here's an example of a recording where the speech is not intelligible, but clearly speech is present. That's a recording from a coffee shop actually nearby here. and there are a few people speaking, and you can sort of tell there are people speaking, and you might even be able to identify one or two of the speakers, but you can't really understand what they're saying. And that's a typical kind of thing that we've got here. So what do people use to be able to recognize speech? Well, our hypothesis is that you pick up on the pitch track of the speech, and there's a particular shape of pitch track which is very characteristic of speech, and may even be characteristic of individual speakers. So what we've been working on is developing a way of extracting the pitch track in this kind of high noise data and using that as a basis for voice detection. So here's another recording, my student Kian-Sub Lee talking to some of his friends.
그래서 기운형도 지금 시작했고, 기운형은 그냥 원래 술 안 마시고.
And this is typical of the kind of data that we're working with. There's a lot of background noise. It was outside. There's some air conditioning running in the background. And what happens when we run a conventional pitch tracker is that there's this strong continuous pitch that it picks up, which is the kind of the rumble of the air conditioning noise. And if we don't take that out, we make a lot of mistakes. So we developed this system of compensating for steady state periodicity to help remove those, and then we get this sort of compensated pitch track that just picks up on the variable pitch track. And that seems to be the important part for helping people recognize that the voice is present, is the non-stationarity of the pitches. So here on a 15-minute test set, which again we had to manually mark as voice present or not, we're getting like almost 90% accuracy for marking speech present or absent, versus something less than 80% when we don't have this compensation piece for these steady background sounds. We can also use these pitch tracks. If they're the accurate pitch tracks, we can use them to enhance the speech just by filtering speech that has a particular periodicity. We've actually been looking at that both for this kind of stuff and for speech recognition as well. Okay. Another thing.
So I have a question.
Yeah.
In the opposite direction. For people concerned with privacy, then is
Yeah.
it easy to add noise and make that kind of unintelligible speech less clear?
That's a nice idea. So we've thought about this problem of how you make it unintelligible if you've got a problem, if you want to do scrambling. And we've spoken about the necessity to have an accurate voice detector to do this, but we haven't actually thought about using that for that process. I think the thing is, like, if you don't want speech to be recognizable, it's very easy to guarantee that you just don't store enough of the waveform to be able to reconstruct it. So you just store the spectrogram or whatever, and then you can't get back that information. But if you want to have a selective thing where sometimes you scramble it because you don't have the confidence that you can record it, and sometimes you don't, then that's the basis that you need. But then you also need the speaker identification on top of that, and that's what we're looking at now. The speaker identification in these high noise conditions is proving pretty hard, and we haven't got a lot of progress on that. Okay, so another thing we wanted to do was to identify where there are the idea of, like, here's my big archive of audio. Can you find events that happen a lot of times here? And we don't know what they're going to be, but just sort of search through them. And that becomes a problem of tractability. That if I wanted to compare every 1 second frame against every other 1 second frame in this 62-hour data set, that would be a lot of comparisons. So to try and speed that up, we're using this hashing approach, which is similar to some work that's been done here by Cormac Hurley, where we describe the audio by these sort of small, discrete hashes, and then rather than having to search linearly through the rest of the database, we can just have a table which says, well, these hashes occur at these different points, and you can quickly check each of those, and it's much, much quicker. The particular fingerprint and hashing technique we're using is this thing from Shazam, which is a company that does music matching over cell phones. And it's based on these sort of prominent time frequency edges, that if it sort of goes through and it filters out a few of these sort of places where energy suddenly starts, and then stores the distance in time and frequency between pairs of these, and that's the basic hash element. And the nice thing about this is that it doesn't really depend on the background noise, it just depends on the strongest pieces of foreground energy, but it's still relatively simple. And so that works extremely well for music detection for them. This is an example of a cell phone ringing or something. Oh, okay, whatever. Seem to have lost the audio. Anyway, but you can see there's this nice pattern in the audio there as well. And then what we can do is, for a piece of audio, we can go through and we can look for recurrences of the hashes on this sort of n-squared matrix of seeing where they come up. So this is like actually a 45-minute recording where there were 3 telephone rings, and so here's one telephone ring, here's another, and here's another, and you see these little matches. And then there's also some music, and it's found these recurrences of particular music tracks that he was listening to. And this is based on this kind of recording, you know, this kind of body-worn-like recording. So the actual repeats are very different. They've got different background noise and different recording conditions, but the fingerprint is robust enough to find that. So it works well when there's exact structure in the audio that repeats, but it doesn't work well for things like he was trying to make it work with the sound of his garage door, which sort of seems like it should be the same, but it's not really tonal enough, and there's enough mechanical variation that it didn't repeat well. So this is there's this kind of trade-off between how precise your hash is. You want it to be reasonably precise so you don't get a lot of spurious hits. But if it's too precise, then you start noticing the difference between different events that you would actually consider to be similar. Okay, so that's sort of the projects we've been doing at the moment. The other stuff we've been looking at in working in the future is looking at these ways of being able to facilitate access to this data. So, yeah.
How did you identify those events?
How do we? Right. So how do we get this? So it's a question of.
In the previous slide, you had a spectrogram, right?
Yeah.
Where you showed these accents. But how do you do the
Yeah.
grouping to find the fundamental unit that you need to find repeating?
Right. So there's no grouping. This is done continuously over the whole audio, and all this. So what we're seeing here is just, you know, each one of these little blue circles is a match between 2 time points. And so they're not, you know, in this particular telephone ring is, you know, maybe 8 or 10 different matches, but they're temporarily clustered. So that's what.
I see. So it's done over the entire time period, and then when you do this match against itself, you find this grouping.
Right, exactly. You get a little cluster of things that come out, and then they sort of form these nice localized events. I mean, you know, this one is interesting. So this is a piece of music, and it's probably, you know, maybe 30 seconds long or longer. It's quite sparse. You know, it hasn't matched itself every 50 milliseconds or whatever. But still, so we haven't done this, but you can imagine having something that recognizes that they cluster together and they're a distinct, consistent event.
Okay.
So, again, to get at this issue of what is this useful for, and can we find these useful applications, it really is important to have a way that has low impact that allows you to look at this data. So we've been looking at trying to build front ends, which I have to say is not really our area of expertise, but it's inescapable for this kind of stuff. So we have this kind of diary interface where we have the audio as a sort of pseudo spectrogram where we're using color, chroma, and intensity to carry different factors. And then we have some extra information here which is actually grabbed from my online diary, and these are the automatically generated segments and labels that go along with this. And again, you know, this alone, the automatic labels alone aren't very good for finding things, but in conjunction with what you had made notes that you were going to do that day anyway, then you can sort of correlate these much better. I'll show you this in a second, this thing actually running. We've been looking at pulling other information into this, such as like looking at the email outbox and seeing when you send emails to sort of, again, remind you exactly what you were doing at a particular time. And one thing we want to do is to synchronize this with pictures, with images, such as things that we might be able to get from the sense cam. So you could actually, again, see what the image was and use that to help you find a particular time point to listen to. And then you click on the audio, click on the spectrogram, you can hear the audio. Okay. We've also been looking at ways of doing thumbnails, like how can you summarize this 10-hour recording into something you could listen to in less than 10 hours. And there's sort of some fun things you can do, like taking half a second every minute and sort of cross-fading them. And that actually gives you an interesting feeling for what's going on, although it's quite impressionistic. It's not really robust. One of our goals for this year is to release some tools for other people to be able to do this. So, because ideally, anyone can make these recordings. Anyone can buy this thing. There's no special hardware here. They can upload them onto their machine. They can make their own recordings. If we can give them the software so they can just drop this in and have this appear, then that sort of doesn't seem like it would be that hard to do. And if we could if we could facilitate other people using this, then maybe we can find out more interesting uses for this kind of technology. Another thing we're obviously thinking about is applying speech recognition to this. I've been involved in this project on meeting recordings, which has mostly speech recognition wouldn't work this kind of data because speech recognition is not good at these sort of high background noises. But there's several groups working on these recordings of meetings, and so this is an example of the meeting data that we collected. And there are a bunch of microphones here on the table, which are recording similar kinds of information that you'd get from a body-worn audio recorder. And so there is progress being made on this kind of task, and we're looking to try and apply some of this on these recordings. Obviously, if you were serious about trying to record speech and transcribe it, you'd probably work a little harder at getting a high-quality signal in the first place, and probably you wouldn't use a single microphone. So we're thinking about trying to use maybe just two of these things just to get at least 2 samples that you could do some kind of blind beamforming on, or even generating a special purpose directional microphone that would actually try and figure out where the speech was and record that at a higher quality. So finally, privacy and security, something that's been a very, always present in this project. I'm hoping we're going to get to talk about this in general a little more because there was a little bit of discussion on email. People very often react very negatively when you say, is it okay if I record our conversation? And of course, it's actually illegal in certain places. I'm not sure if it's legal in Washington or not, in Washington State. There's this interesting project that Deb Roy at the Media Lab is doing where he's recording everything in his house, with his kid growing up to see if he can figure out how the kid bootstraps language. And they have a few approaches where they have this thing where they have an oops button that they can delete, the last minute's worth of audio every time they get something they feel they don't want to record. There was this very interesting talk at the original CARPE workshop in 2004 by Golubchik when she was talking about the issues that once you start recording this data, there are all these kind of interesting legal things that even if you don't want it to be used, it can be subpoenaed. And so, you have to worry about exactly what you're exposing yourself to if you collect this data. So the access to recordings is very sensitive, but so is the preservation. I mean, one of the things that I do when I make these recordings is I'm kind of paranoid about making copies of them because, if you do lose it, you never get the chance to record it again. And that's kind of an interesting tension between wanting to have redundancy, wanting to make sure no one else can access the data. So at the moment, the data I have recorded is all on DVDs and a disk, but they're offline. They're not on the net. And my student who's made his recordings, similarly, his data is not on our servers anywhere. He doesn't, I had to get his permission to use the little chunk that I played you earlier. Of course, if we're really worried about speech, we can just make sure that the speech we store is not intelligible. And in fact, maybe we could actually run the speech recognizer on the original data, then throw it away. Then you've got this kind of semi-reliable transcript, because speech recognizers make a lot of mistakes. So if you can say, oh, that's not what I said at all, the speech recognizer is not going to say, no, that's definitely what you said, because no one believes that. So that's kind of interesting middle ground, maybe, if that works out. Different approaches to try and, preserve different levels of access and security and different ways of. There are a lot of privacy experts think about these kinds of problems. All right. So conclusion: personal audio is something that we can easily collect and manage. I mean, very easily. It's $100 to buy a recorder or less. But the problem is making it useful. We've looked at these problems, the task of segmentation, which turns out to be pretty successful. We looked at voice detection, which is working pretty well. It's a question that's sort of a question of how far down, how noisy it has to be before you don't care whether the voice is there or not. And we're looking at speaker identification, but that's still work in progress. This problem of finding these arbitrary repeating events, I think, is kind of interesting. Again, we've just got this working on a scale of an hour-long recording. I think it would be really nice when we can actually make this work on, hundreds of hours and see what kind of things come out. We haven't quite got that going yet. And then we're working on these distribution of tools. So just in the last second or so, this is the interface I showed you here with the automatically generated labels and the diary events. And then so you can just click here, and I don't know what's happening, but it does actually play back stuff. Do we know why we're not getting audio? Okay, whatever. The audio's died, but you can click and you can get this. This stuff was written. This is a very kind of shaky thing that I wrote in TCL. What CanSub has done is he's re-implemented this in Java, which is something which is much more cross-platform and something we can adapt and and distribute. And this is going to be the basis of our other tools that we hope to make available later this year. Okay, that's it. Any questions?
In the interest of time, Alan, you must start getting set up, and Dan just takes as long as it takes Alan to set up.
Yeah, I'm sorry. I took half an hour as well. It seems like we're not doing very well. Yeah. Okay. Any questions?
That's really interesting. I was wondering if you've been thinking about. So for example, understanding the environmental characteristics can play a very interesting role in other applications. So in one of the research projects I'm working on, the sound characteristics are very important for us to know, to figure out how do we get in touch with this person. So I'm working in context-aware routing of messages. So this company is very interested in how do we get in touch with this person, but they need to know whether this person is in a mall, in a library, or maybe this person is having dinner. So they want to figure out how do we route this message. So you need to have some understanding of what is the sound environment, so that if it's quiet, maybe I can call them.
Yeah.
If it's extremely loud, maybe I shouldn't. So maybe having this understanding of what's going on can help in applications such as that.
Right.
The other issue I was thinking about is that a traditional problem in speech recognition is that you do recognition in very clean environments, right? But you do it for one person. I was wondering if you have a history of recordings and it turns out that there's repetitiveness in location, could it be that you could train for those environments for this person? Is that something that you think that can happen?
That's a nice idea. Yeah, that's a big issue. That in general, in any kind of statistical modeling, the more you know about, the more closely you can characterize the interference, the better you can do. And so, if you suddenly have this history available, you can suddenly get as much. Yeah. That's a great idea. That's a very smart idea.